This is the first lecture for Module 1 of Unit 4. Unit 4 concerns chemical equilibrium. Let's begin with the restatement of something you looked at in the first unit, which is LeChalier's principle. If a stress is applied to any system at equilibrium, the composition of the system will change to counteract the applied stress. We have seen this statement before. I will add that the change will act to restore equilibrium. In this unit, we will look at chemical equilibrium and how LeChalier's principle affects changes to chemical equilibrium, or to systems at equilibrium. To think about chemical equilibrium, let's begin by considering something you've seen before. Consider a chemical equilibrium between reactants and products, such as a weak acid and water. Take acetic acid, for example. Acetic acid, you know from your first general chemistry course, is a weak acid. So, when placed into water, it does not lose all of its protons to water molecules, but some, and an equilibrium is established in which you have both reactant and products present, and forward and reverse reaction going on at the same time. The result, if you may remember, is that only a small percentage of the acetic acid molecules have broken apart to form protons and acetate ions, or hydronium and acetate ions. Note the balanced chemical equation for this can be represented by including water and showing the formation of hydronium when H transfers from the acetic acid to water, or this reaction, this equilibrium, may be shown by the more conventional approach in which an H plus is shown on the right hand side and no H2O appears on the left hand side. Students should remember that these two ways of writing this equilibrium are equivalent. Right. So again, a solution of acetic acid actually holds a mix of ions and neutral molecules, products and reactants. You will remember the left side is favored. There are more neutral molecules. This is an example of an equilibrium you've already seen. Okay, so to summarize, at equilibrium, both forward and reverse reactions are going on. The forward rate is equal to the reverse rate. A balance exists between the reactants and products. Therefore, a quantity called the reaction quotient is constant. What is the reaction quotient? For any reaction, if big A and big B react to make big C and big D, and the numbers in the balanced chemical equations are the small letters A, B, C, and D, the reaction quotient is an expression in which concentration of product appears in the numerator, and here we see brackets used to represent molar concentrations, raised to their stoichiometric coefficients. Likewise, reactants appear in the denominator, concentrations of reactants, raised to their stoichiometric coefficients. This quantity, this ratio of product and reactant concentrations raised to powers, is a constant at equilibrium. The reaction quotient Q is a constant. We write Q equals K, where K is a constant at equilibrium. All right. At equilibrium, then, again, K equals Q, or K equals the ratio of product concentrations raised to power over reactant concentrations raised to powers. This is called the equilibrium equation, or sometimes the equilibrium law. Alright, so K equals Q at equilibrium. What substances appear at Q? What appears in the equilibrium expression? Not all things in a reaction necessarily appear in the equilibrium expression. Things that do appear are solutes in any solution. In particular, we will look at aqueous solutions, but in any solution in particular, and gases. Solvents, pure solids, and pure liquids do not, in general, appear in equilibrium expressions. So here is the equilibrium equation for acetic acid and water again. Acetic acid and water goes to hydronium and acetate, or acetic acid goes to H plus and acetate. And again, these two are different ways of writing the same process. At equilibrium, the constant K is equal to H plus concentration times acetate concentration over acetic acid concentration. Notice that you could use this form to write down the equilibrium law. This is an expression that occurs in aqueous solution, or a process that occurs in aqueous solution. So the solvent water does not appear. All right, here are some examples you should attempt before continuing. Write down the equilibrium law for, or equilibrium equation for 2HCl goes to H2 plus Cl2, where all species are gases. Write down the equilibrium law for solid calcium sulfate reacts with sulfur dioxide gas to make solid calcium sulfide and carbon dioxide gas. And write down the equilibrium expression for this reaction in aqueous solution below. All species, again, are within water. Alright, you should stop at the presentation and attempt these before continuing. For the three problems given, here are the answers. K is concentration of H2 times concentration of Cl2 over concentration of HCl squared. Here we see the power of 2 appear because of the coefficient of 2 in front of HCl in the balanced equation. Notice that the C that is used here, or a subscript that appear here, often means concentrations and appears in equilibrium expressions for gases. You could also write Kc equals concentration of CO2 gas over concentration of SO2 gas for the second reaction. Solids, remember, do not appear in equilibrium laws. So only the concentrations of the gases appear. Alright, for the third one we have IO3, which you will remember is iodate to the 7th power times H plus to the 7th power. Excuse me, since those are reactants, they should appear in the denominator. You see the correct form here. And iodine concentration raised to the 1st power, and H5IO6 raised to the 5th power appear in the numerator. Alright, this should be the correct equilibrium expression for problem C. Let's consider the meaning of the magnitude of K. Here we see once again the equilibrium equation for acetic acid. Turns out the value of K for this is 1.8 times 10 to the negative 5. So in any situation in which you have balance, the denominator of this expression must be much larger than the numerator. K is much less than 1. So the acetic acid concentration is much larger than the product of the H plus and acetate concentrations. You remember you were told the left side of this reaction is favored. This is consistent with a small value of K. A small k means the left side of a reactant is favored, and you will mostly have reactants in your mixture. A large K would mean the right-hand side is favored and that there are mostly products in your mixture. So, armed with that knowledge, answer the question, is the K for dissociation of HCl in water larger or smaller than 1? Again, this is for dissociation of HCl in water. You know HCl is a strong acid, unlike acetic acid. So, you were originally told that this reaction essentially goes to solute completion and all the HCl's break up into H plus and Cl minus. So K for this reaction must be very large. In fact, the value of K for this reaction is 1.3 times 10 to the 6. Products are much more favored than HCl. And it is, for most applications, safe to assume that all the HCl dissociates. This concludes the first lecture on equilibrium.